So kuklov from City University of New York. So I think so Anatoly is known to everybody here for his outstanding contributions in a lot of questions, especially with the Born algorithm Monte Carlo. Thank you very much for coming.
Okay, thank you for the introduction and thank you for the invitation. So today I'll be talking about superclimbing dislocation. So what is unknown, and definitely I have to introduce what it actually means. This work is done together with graduate student Daria Lenikova. I'll give, as I promised, introduction, explain what superclimb means. First, maybe what climb means, then what superclimb means. Then introduce action and do a formulation for this action. Then we will describe linear response, most interesting feature, so-called giant isochoric compressibility, which makes an example of non-Latinger liquid behavior.
Isochoric is constant volume.
Yes.
How you compress constant volume?
Yeah. Compression in the sense of adding particles to finite volume. This is what it means. It's like derivative with respect to chemical potential volume. Then I'll talk about nonlinear responses in this model, just responses, because they're very different. And finally, I will talk about quite interesting peculiar feature, resonance superclimb. And as we believe, it will present a new class of quantum phase transition in 2D, which is different from postulus Paulus and Isaac. Okay, so what is dislocation, first of all? Let's imagine you have ideal crystal. And you, let's say, consisting of ideal planes, and let's say you cut half of the plane and heal the crystal in this part. What you are left with is extra half plane and the line of the dislocation going into the screen. So this topological defect can perform two types of motion. It's called edge dislocation. One is glide, when this half plane switches with this one and just simply moves around and translates the upper part of the crystal. And it can also perform superclimb. What do I mean by superclimb? In standard metals, there is no superclimb. There is just climb. Climb which can exist at high temperature. And it's supported by adding matter, let's say either adding new lines of atoms or removing these lines. And so this dislocation edge will move up and down. So you need, it's so-called non-conservative motion of dislocation, and you need transfer of matter toward the core. So by superclimb, I mean that in helium-4, certain dislocations were observed to have superfluid core. It means that matter can be transferred to the along the core, and consequently you can construct a move up and down due to purely superfluid transport. You don't need diffusion. So this type of motion can exist practically at zero temperature. So practical. I'll explain what it means. This is what we mean by superclimb. Climb supported by superfluidity along the core. Okay. So what is the evidence for superclimbing dislocation? This is an example of typical helium-4 configuration in a box, which we simulated. And this blue cloud is so-called condensate matter. It means that this is the core of the dislocation. And around this core, you see finite density of Bose-Einstein condensate. It means that infinite cycles, also infinite is finite sample, let's say superfluid cycles, winding cycles occur along the core. But what is most interesting for this system is that applying chemical potential, you can change the position of the core. So you can move it to the right or to the left. And this is what we observe. Essentially, you have strange color. Okay, something wrong with the red. So what you see in here is a response of the position of the core versus applied chemical potential. And you see that core of the dislocation moves in response to the chemical potential. It means that you add more matter or subtract matter by simply building or reducing the size of the extra plane, half plane of the dislocation, which creates edge.
Just can I ask a few
Sure.
Go back to the picture previously.
Yes.
So the blue are the condensate atoms?
The blue is a so-called condensate map. It's not additional atoms, but the same atoms actually perform participate in crystal formation and also create infinite cycles, exchange cycles.
I see. And if there's no dislocation there,
No, there
there's
is.
no blue, if there was no dislocation,
Yeah.
there'd be no
No,
condensate.
no.
How do you measure the superfluid component?
Oh, but this is separately relation. Basically, we measure fluctuations of Weinberg numbers in spatial direction, and it's.
So does it mean that if you have many dislocations, your crystal is superfluid when they overlap and percolate?
I'm trying to fix color.
Oh, okay, just right time. Well, this is a good question. Basically, I'm not touching right now this question, what happens to the crystal as a whole, because you need definitely three-dimensional network. But this is a separate topic.
No, if you had just 2D edge dislocations, like so, I'm considering only a 2D picture, and you just have a lot of them. So
Yeah.
these blue regions overlap.
Yes, the essentially crystal will be superfluid, but you need really great density of dislocations to make it happen. Usually, the density is such that there is no overlap.
Sorry, one more stupid question. Can you plastically deform your crystal so you produce a lot of dislocations? Is there any experimental way of doing
Yes,
that?
yes.
So you could dynamically induce more superfluid by creating dislocations, by shearing.
Yes, but not all the dislocations are superfluid. This is important. This type of dislocation with Burger's vector along high symmetry axis is superfluid, but other dislocations, smaller Burger's vector lying in the basal plane, HCP structure, are not superfluid.
What is the actual model that you are considering, the Hamiltonian?
I'll write it down. I show it right now. Once Igor finishes fixing colors, I'll show it.
It's getting worse, it's getting blue. This is broken, yeah, it's getting more and more blue.
Ah, it's okay. Will be like talking blue.
Another question. Because we recorded this maybe about the power. Where do the atoms come from?
Where what?
Where do the extra atoms come from when you remove your
Of course, these simulations are grand canonical simulations.
No, but in real life?
In real life, presumption is that dislocation touches, let's say, comes out and is in a contact with the fluid or some bigger reservoir. And this is, I'll show you the experiment, which actually we believe has, well, I would say theory, our theory has much to do with the actual experiment.
So atoms migrate to that point, and
I'll show
join
you
the
the picture. So I'll show you the picture.
So those are just atoms? The dots are the atoms, right? And those are the
The
helium?
atoms, okay, the dots is instantaneous configuration, instantaneous position of atoms. It's like snapshot.
And there's no other, just those are the only atoms in the system.
Right.
And then some of them can be superfluid or have a component.
Yes. If you wait long enough, basically this configuration you can view this way. Atoms kind of sit, and once in a while they perform infinite cycle, exchanging the whole system. And condensate map, I can actually describe details how condensate map is constructed, but probably later on. It's just technical. Okay. So this is the experiment. Actually, they were conducted by Ray and Hellock, and the idea is pretty simple. Let's imagine you have solid helium-4, and you would like to pump liquid helium-4 through the solid. So how can you do this? You insert Vicar electrodes and pump liquid into electrodes. The point is that at high pressure, when helium-4 solidifies in free space, it stays liquid inside the Vicar. Vicar is a glass, small pores. And so if you apply somehow chemical potential, you basically, and there are some channels, dislocations, they can flow from one electrode to another. And essentially this is what was observed. The point is that there was overcritical current relaxation. I'll explain what it means. Flow vanishes below 0.5, 0.6 Kelvin, which is way below lambda point. So this excludes completely macroscopic channels. So let's say some cracks inside. Another interesting feature is that huge fraction of helium-4 was accumulated in a uniform manner, which is not consistent with any plastic flow. It's just only superfluid way of accumulating.
Why do you say you exclude cracks and things like this? Because this is the high pressure, right?
Yeah.
So, yeah, simply I'd like you to
Yeah. So if it were,
I'm not used to this field, and
yeah.
I don't understand the statement.
Okay. If there were a macroscopic crack, let's say micron size, then flow would exist up to lambda point, which is 2-something degrees. But flow vanishes 4 times lower temperatures, 3 to 4 times lower temperatures. It means that if there are channels, but they are macroscopic size, like nanosize, you can say these are channels or dislocations. It's how
So it gives you an upper limit on the size of whatever channels these are.
Yeah, I would say if you go to size, let's say 100 nanometers, it would be already 2 kelvins. But it definitely
Can
the
you
size.
estimate the size by knowing, I think this is what you need to know is surface energy for
Yeah.
helium droplets?
Yes. In principle, you can determine the size of the macroscopic channel, let's say 3-grain contact. Yeah, you know energies, you can determine that. But apparently, given these numbers, these channels do not exist.
So
But
the
what is
capillary
typical
force-
size you get?
Huh?
What is the typical size you get if you do this exercise? I just
Oh, you mean for these temperatures?
yeah.
Few angstroms. Few angstroms.
Okay.
Few angstroms. Okay. So this is typical data. Okay, it's supposed to be black and red. So pressure was applied to one electrode, and this is the response of the second electrode. What you see is essentially linear in time dependence of the pressure relaxation. Linear in time means it's overcritical current at fixed velocity, no matter what the pressure difference is. This is overcritical current. These two curves show how pressure inside changes. Let's say at one part of the sample and another part of the sample. It does change. It means matter accumulates inside, but accumulates uniformly. The difference between two gauges is essentially the same. So there is no way to achieve this effect by plastic deformation. Classical plastic deformation means that you need pressure difference, like a flow, to create something.
But this is just a single compression.
No,
Not compression.
No, it's not compression. It's look, you put pressure to the liquid in here, and liquid flows from here to here. So these two pressures relax, and simultaneously pressure in the sample here and here changes, but changes uniformly. There is no time dependence in pressure difference between these two electrons.
But suppose you reverse P2 and P1
Yes, it goes
periodically.
back. It goes back. It goes back.
Maybe you have quantum teleportation with it.
Quite possible. Quite possible. Okay. So we will concentrate, well, it's important that there is significant mass accumulation in the bulk, and we believe this is clear-cut evidence for superclimb I was introducing before. How mass is accumulated essentially in building extra planes of the dislocations under the applied chemical damage.
Is there any reason to believe that boundary, well, the age of the sample plays any role, or it's Is there anything happening at the edges?
Well, it's hard to say where it's happening, but the amount of matter transferred, it could be that it's purely on edges. It's not really known. There is no kind of size measurements. It's not easy to change, to vary size of the cell and see how the result depends on size of the cell. But let's say, what is the simplest assumption? We assume this is bulk effect. So, okay, it could be something going on in the process.
But it also means that if you wait long enough, basically you eliminate all dislocations and then it should stop.
Well, it's a good point, good question, but the problem is that eliminating all the dislocations is not easy, because they entangle, there is some dynamics going on, and new dislocations could be created, like there are loops, so-called prismatic loops, loopy dislocations, and if you apply chemical potential, they can inflate. Actually,
right, so they inflate and basically they exit on the surface. So again, hypothetically, if you wait long enough, you just anneal the crystal and becomes ideal.
Maybe it's a good suggestion for the experiment.
No, I'm just curious, what would be the time scale? Can you?
Well, the typical time scale of the experiments, here you see it's in minutes, actually, as far as I know from Bob, they waited 1 day and flow didn't stop. So.
I mean, does it change in time or?
There are some changes, yes, indeed. For certain samples, if he waits long enough, he sees changes of the slope, which could be interpreted as, let's say, some channels go away, or maybe some channels go into the play. So, yes.
Because you don't produce shear or distortion here, so you don't create new dislocations. I mean, in the idea geometry.
Yes, you don't, I agree. But, in fact, you never know how shear is working there, because crystal is not uniform, and in principle shear could be also involved there. And the threshold for shear is pretty small there. But it's, I agree, it's very interesting questions, behavior of network of dislocations, their dynamics, and how it's intertwined with superfluidity. In this talk I'll address just behavior of single dislocation. Okay, so basically sketchy, this is what happens. Let's say this is the extra edge, extra plane, and essentially it can move up and down. So under the application of chemical potential. How to describe the system? We use string model. Essentially we describe position of the edge by some coordinate along the dislocation. And in addition, we need to introduce variables which describe superfluidity along the core. This is the model. Okay, this is the Hamiltonian, so it contains superfluid part, dislocation part. We need to calculate partition function, and superfluid part consists of standard bariter. This is in hydrodynamical variables. This is the kinetic energy of the flux. This is the compressibility term. So what these integers are? These integers are introduced in order to explicitly account for the definition of the phase as 2 pi, modulo 2 pi, okay, to allow phase sweeps. It's a standard action. If this term were not present, it would be completely superfluid action. We know what happens in here. Two-dimensional Kosterlitz-Taulis transition in imaginary time, let's say 1 + 1 dimension. But there is an interaction with dislocations. What this term actually means? It means that the matter which comes along the dislocation, if density changes, can be absorbed into the building the edge. So in principle, you can increase density infinitely, and undo this action by simply shifting the dislocation. This is what it means. So it's some sort of discrete gauge transformation. Look, if you change y by 1 and rho by 1, essentially nothing changes. What prevents you to do this is this term, which is Peierls potential, because dislocation lives in the crystal lattice. So shifting edge by 1 unit changes time. Okay.
Is this a lattice model? Is this Hamiltonian is defined on some sort of lattice?
Yeah, sure. We simulate it on the lattice. Simulations usually done on the lattice. And in crystal there is a lattice. So lattice, with respect to shifting the edge by the period of the lattice, and of course we broke the dislocation into final segments and did simulations of finite sine Gordon.
And so by the filling, you mean the filling with respect to the lot size of this
Yes.
slide?
Yes. So this is filling factor, some constant. What is subtracted in here? We subtract essentially, it's like subtraction of chemical potential. We don't know how chemical potential, with respect to what it's defined. Dislocation can be slanted. If this is, let's say, if you have horizontal Peierls valleys, and if dislocation is not in a Peierls valley, but let's say slanted at some angle, so you have extra kinks on it, and you hold it by the end, Berry term shouldn't care how you prepare this dislocation. So this is what is subtracted. This is kind of the initial position of the edge. So we consider response with respect to the initial position of the edge.
Is there a particular direction it likes to move in, the chemical potential?
Well, it depends on chemical potential. Actually, you could put it here, and then it's by simple Gaussian nature of the action can be considered as force applied to the dislocation edge. And depending on the direction of, let's say, sign of chemical potential, it can move up and down. Yeah. So let me give brief qualitative description of what to expect from this seemingly complex action, because it's a combination of U1 action interacting with sine Gordon, so what to expect from that. So obviously, if temperature is very low, it's natural to expect that cosine potential is relevant. It means that we can expand it. Let's forget about slanting, that this term is 0. So we expand cosine term with respect to small values of y, right? And you get purely Gaussian action. If you do this, you will get this. You say, okay, why you eliminated y? Because y is gapped now. We don't care about y. And we come back to simple superfluid action, U1 action. And what we know is that this action describes sound, standard stuff. And let's say the amount of matter which can enter a sample by the mechanism of moving the dislocation is essentially negligible. So basically the number, this is called isochoric compressibility, the derivative with respect to chemical potential total number of atoms. And it's essentially inversely proportional to the square of the size of the dislocation.
If you integrate out instead rho and phi, wouldn't you get some sort of a theory for a self-interacting string? So if you, well, in the
Yes.
previous
I'll show you what we've done. We integrated actually. You will see in dual formulation, you will see the action with long-range interactions.
But I was also wondering about the gauge invariance of this, in some sense. So, you know, of the original action.
Of the original?
Yes. So, so is there an issue at all? I mean, that.
I don't see any issue.
So if you do perform a gauge transform, let's say with the phi's, so do you have to do anything with the y at all?
Why should you do it? You mean time-independent gauge transformation? It's not affecting this term. So this term is...
So, I mean, if the phi's were not important at all, so I could just shift the integral over, the path integral over rho, over rho, and
Right.
eliminate dependence on y at all, and I would just decouple the two models.
Yeah.
So, there must be some sort of
I don't see any problem. It will generate some sort of, well, first of all, if you neglect that, this term will be completely integrated out, so you'll just left with this section.
So why are you not left with this section, which is just the sine Gordon type theory, right? So or no?
Well, yeah, essentially you will end up with sine Gordon type action if, let's say, if fluctuation of density is kind of large. You don't care about building the method, but it's kind of a situation when you don't. It's kind of a limit when there is no superfluidity, but instead you have somehow large fluctuation of matter, which comes from nowhere. It's not quite physical. And
No, sorry, I was just trying to understand formally this model. So you have an integral over rho, right? So you can just perform a change of variables and just consider rho minus y.
But look what happens. If you say, okay, this term, let's say this is 0, then what happens from here is essentially that derivative of rho should be 0. So it means that there is no dynamics of rho, and this integration of a rho doesn't really make much sense. Right? So you have to consider, it means that you cannot bring matter into the, to build the dislocation, to make it free. Okay, so if, once again, so we, if there is no, let's say, y, we have normal sound. If there is high temperature, let's say, cosine term may be expected to become irrelevant. And then what you're left in combination of this action and this action, and your Gaussian action, and essentially sound is now replaced by quite anomalous dispersion. If you do simple elimination and ignore these terms and purely Gaussian elimination, you'll see that spectrum of this in real time is anomalous. And the response of the system, if you try to boost some amount of matter, you'll see is anomalously large. So basically you can accumulate the amount of matter independent of the density of dislocations.
Sorry, in what sense is it anomalous?
It's anomalous in the sense that it's anomalous in the sense that it's not sound wave. It should be.
It's not linear, right?
It's not linear. It's Q squared.
It's like bending waves, or what?
Yeah, it's like very soft bending waves. Yes.
So it's not superfluid.
In the dynamical sense, yes, it's not superfluid. But in the sense that your dislocation is of finite size, there is a threshold, but which is a macroscopically small threshold for breaking the superfluidity. But for any finite dislocation, in principle, you can support flow if the critical current.
There is a finite critical current.
Finite critical.
I'm trying to understand Victor's question. I think I have the same trouble. If there is no gradient rho term, you don't see how, because you are taking path integral over rho, right?
I'm taking over phi over rho over y. I'll show you the result of this exact integration.
Right, but it seems that you just integrate out rho without dynamics, so it will probably produce a gradient phi in time squared, like in x. But I don't see any coupling between y, which remains.
No. It's time. It's time dependence. It's not x.
I understand. So if you integrate out rho, you will get this term squared probably, grad phi.
Yeah.
Kind and so on. But there is no coupling with y.
No. You have to shift y. You will get y under the integral. There is a
Gaussian integral, doesn't it?
Yes. Yeah, the Gaussian integral. Yeah. But there are phase slips terms which cannot be really integrated out right away. Okay, let me show you full action where all this rho and phi and y are integrated out. So this is the original action, and if you do the Villain approximation for cosine term, it becomes completely Gaussian. But instead, you have to consider now integer currents along x along tau, and also integer value of the this variable phi. Now, if you do the integration of rho, y, and phi, you end up with this type of action. So basically, what you have now is integer variables along x direction of the bonds, time direction of the bonds, and also integer value of the scalar variable, which is not constrained by any relation. And instead of the integral, you have to do finite sum. Okay. So this is the and you generate long-range interaction between a combination of space currents and dual variables for sine Gordon. And we did simulations for string pinned at the ends, so we have to satisfy boundary conditions that there is no displacement at the ends. And this produces essentially the effective interaction, which automatically ensures this condition. Okay.
So what is the physical meaning of P variance?
P is ensuring sine Gordon invariance. It's a domain approximation. Essentially, instead of treating cosine, you can introduce this and sum over this variable so that this term retains invariance of sine original.
There is no simple physical meaning, like M are currents, right?
No. Well, you can say it this way. So basically, you offer the dislocation to have positions at some integer values along the Peierls barrier. It could be first position when p is 0, pi is 0, it's first position, or next position, or next position. And if you don't sum over this, it will be essentially gapped string at some position. But if you sum over them, you equally well offer all these positions, and you restore the original discrete invariance of the system with respect to the position of the point.
So you don't consider, let's say, distortion of the dislocation direction perpendicular to the screen.
No. Yeah. Glide is not considered.
But usually the pile dislocation for the glide is much weaker than.
Yeah, this is simplified model, which in principle we should consider two variables: displacement perpendicular, but this is just the model. Yes, we believe it picks up already main features. Yeah.
So that's why the ends are pinned down. So there's that's the condition of no glide.
Oh no! It can perform glide. So basically, what we say is the following: that if dislocation kind of is a line, but we don't allow these ends to move, right? It could be slanted at some angle, let's say y, and we also don't consider motion in z direction. But in principle, it's possible. This model, this approach allows including glide as well. Yeah.
Sorry, may I ask another question about the villain? So usually, if you do it with, let's say, vortices, basically it's a duality transform when you go from phase to number of particles. So what is dual to y? What is the physical meaning? Well, basically what Anton is asking. So there is some basically dual variable to y, right?
Right.
So it must have
okay.
some sort of
Dual variable meaning of y is the duality between y and pi is the following. If string is gapped, y is small, right? So basically, yeah. If yeah, but so basically, so you can say it, yeah. But if
so it's momentum of the strings probably, right? So because y is the coordinate of the string, so if it's gapped, it does move around. So
it does move around, but the it's sort of, it's not really in a direct sense of duality how we got used to superfluidity, but in a sense of just variable which can be equally well used, and you can express all the correlators in terms of this variable equally well as that variable, and let's say fluctuations, big fluctuations of y actually do imply fluctuations of no. Fluctuations of y essentially leads to the fact that pi can be taken 0.
So it's Heisenberg uncertainty related.
Yeah, yeah, something, yeah.
So relation important then.
Yeah. It's the same unit, the same. Yeah. So basically, this is the model. Of course, analytically, it's not possible to handle this action. So responses. How to construct responses? We consider two responses. First is the response on chemical potential of external forces, which is just simple ratio of deformation with respect to small force, or whatever force it is. It can be expressed as a first derivative with respect to the partition function. And also differential response, which is expressed as a two-point correlator of y. And of course, these two responses are related to each other, it's obvious. And furthermore, for small force or small chemical potential, they coincide. So within linear response, it's just single response. Yeah. And basically, it means that we know the displacement of the string translates into the accumulated matter. So basically, these two responses are related to finite accumulation of matter, finite number of atoms transferred, or finite chemical potential, or simple derivative, which is compressibility. And we can also consider superfluid response in terms of winding numbers in space direction and in time direction, which is compressibility. The point is that this term and this term is essentially the same. Within the proportionality coefficient are the same. So we have three quantities to measure. And furthermore, we can also introduce renormalized speed of sound. It's a ratio of renormalized superfluid stiffness and compressibility. So since we do thermodynamical Monte Carlo, no dynamics is involved, we consider this quantity as a kind of measure of critical velocity. We will see that under certain conditions, kappa can become anomalously large. It means that critical velocity drops.
So when you have this, maybe it's not related, when you have this quadratic dispersion, right, does it mean that the speed of sound is 0?
No, for finite sample it is not 0. We consider finite size, we essentially consider finite size effects.
I see.
Yes, of course, if you take infinite dislocation.
So you're saying the thermodynamic limit, if you have quadratic dispersion, physical current would be 0.
Okay, so now linear response. So basically what we have in here, we plotted one of the measured quantities, R2, or if you wish, compressibility. And it's a function of temperature. For different biases, I mean for different slanting, one end of the dislocation with respect to Poyle's minima. So this is called the bias. We see that these responses, except for just quite anomalous behavior of single king, there is just two valleys, we observe kind of intermediate region where the giant isochoric compressibility exists, and at low temperature it's supposed to be suppressed. And this curve is just how superfluid fraction behaves as a function of temperature. So suppression of the isochoric effect happens where superfluidity is well defined. The nature of this peak is a separate question. I will not be discussing it here, unless later on we can talk about this. Okay, now how compressibility behaves as a function of size of the dislocation. You see, we did starting from 10, 20, 30, 40, up to 100. We see that superfluidity for so low temperatures is not affected much. But compressibility is affected dramatically. It's a function of size of the system. And essentially, if we measure how it scales with the size, you'll see some power law. This power law is true only when long-range interaction, I'll mention what it is zero. For finite long-range interaction, it can actually take any value between 1 and 2. Now, what the long-range interaction? Actually, I didn't mention it at the beginning. Dislocation is embedded in three-dimensional crystal. So any kink on the dislocation, two kinks, let's say, on dislocation, exchange phonons through the bulk. If you eliminate the bulk, you will generate 1 over R interaction, effective Coulomb interaction. And so I'm referring to the giant compressibility effect as a function of this coefficient long-range interaction. So long-range interaction reduces giant compressibility. It doesn't kill compressibility completely, but it reduces.
Shouldn't it be a log of R interaction?
Say it again?
Shouldn't it be logarithmic interaction between the dislocation?
No, it's not between dislocations. It's between the kinks on the single dislocation. So you have, let's say, something like that. And this is R. And this interaction is 1 over R.
So it's 3D Coulomb, essentially. 3D Coulomb.
3D Coulomb,
Not
yes.
2D.
3D
not
Coulomb
1D.
acting on kinks along this one-dimensional dislocation.
Does it want to get rid of it, or does it want to attract? Or
A kink, anti-kink want to attract. Two kinks would like to repel each other.
and is there any spontaneous formation of these kinks, or just?
Well, if you have slanted deformation, you will have finite density of kinks already, because the number is fixed by geometry. If it's non-slanted, there is no spontaneous creation. And furthermore, it can be shown that for any finite G, there is no post-Staurus transition in the system. So 1 over R interaction kills post-Staurus transition. Okay, now about nonlinear response. So let's say if you increase applied chemical potential, you can immediately see that two responses become different. And what is shown here, it's supposed to be green, okay, that two responses, R2 and compressibility, defined in terms of Random numbers and reduced by maximum value, everything is reduced by the response of free string up to 1. So you can ignore Sine-Gordon, you can solve the problem exactly, you can calculate these responses, and essentially R2 and kappa are the same, one and the same. Okay, the important issue is that when nonlinear response begins. So what determines nonlinearity? Is it of the order of 1? The point is that criticality of the behavior is determined by the inverse size of the dislocation. So it's macroscopically small threshold. It means that dislocation, large dislocation, is essentially nonlinear object. Let me explain why. So let's imagine you apply force to the dislocation and create a pair of kink-anti-kink, separated by distance x. You spend so much work, which is energy of creation this pair of kink-anti-kink, some finite number. And when you're too close, it's 0. When you separate it by the size of the solitone, it will be some finite value. but you actually, this how amount of energy you lost, but you gained energy by progressing the edge of the dislocation by Burger's vector forward and separating by distance x. This is the amount of work done by this force. So if you see that eventually, if the size of the dislocation is large enough, you can get this work negative anyway. And this is the critical force which is able to create pairs of kings and anti-kings. And yeah, it's also supposed to be. So there is a large range of chemical potentials where dislocation should behave non-linearly. Up to the upper value determined by the Peierls potential, when the Peierls potential becomes completely slanted and no minima exists. This point was actually emphasized by Hirsch and Lotta more than 50 years ago, that there is a barrier essentially for creating kings. So you can have so small critical potential for inducing the nonlinearity, but you have to overcome this huge and large barrier.
Is it much different from superfluids and one-dimensional superfluids and phase slips at fixed currents?
Yeah, I guess it's very similar because the scaling is essentially at zero temperature is essentially the same. So the size of the system determines what is the critical rotation principle, but you cannot really achieve introduction of vortices into the system. Yeah, it's basically this is the threshold for effective creation of instantons.
If you have another dislocation nearby, it could lower that variable, right?
Oh yeah, so interaction with dislocation, several dislocations, given long-range interaction between them, it's quite interesting subject, and we're working on this now. Yeah. Now, a quite interesting phenomenon which we observed in simulations, so-called resonance superclimb, that as we believe quite not well understood the new universality of the behavior. So let's say what we have in here is a plot of the responses R1 and R2 as a function of chemical potential at fixed temperatures for different sizes, slightly different temperatures, for different sizes. Size of the dislocation 40 units and 80 units. What we see in here, this is the curve for 40, and this is the curve for 80 units. We see quite nice periodicity in the responses, which which is consistent with the simple creation. This is where first pair is created, this is second pair, this is third pair, and so on. So quite nice periodicity in terms of the gap. So it gives you the measure of the gap, essentially. And you cannot see such periodicity for size 40 because we need to apply essentially a much larger chemical potential.
So what does it mean, the size of the dislocation? It's the system size, essentially?
No, yeah, dislocation line. Just it's pinned, yeah.
And it's periodic boundary conditions, or what?
Pinned boundary.
Ah, pinned boundary.
Yeah.
But can the kink exit the system somehow? If you have, let's say,
no, you create pairs, kink, anti-kink. They can recombine, of course.
but they cannot exit or end
No.
at the boundary.
Hard boundary. So responses are very much different, right? So you see these peaks. And we ask a question, what is the scaling behavior, so to call, of the first peak? The question is how height of this peak, first peak, scales the size of the dislocation and oh yes, I should have mentioned that basically peak in the compressibility translates in the dip in the critical velocity, right, as a function of chemical potential. So if this thing jumps up in some finite range, you would expect to see that critical velocity exhibits some dip. So we ask, and what is in here is superfluid density. Superfluid density is essentially unaffected. What is affected is compressibility and critical velocity. This dip is quite important. We believe it was recently observed by Hella. So I'll show you some pictures. Yeah. So this is I'll talk in conjunction with this experiment, recent experiment.
What's again determines position of the peak?
Position of the peak is determined by size of the dislocation, unpinned part of the dislocation, and gap. Virus gap. So it's essentially a ratio of the gap versus the size.
How do they vary? They vary the chemical potential of the experiment?
No, they vary temperature, but I'll show you that this peak shows up in temperature dependence as well. Okay, so here's the temperature dependence. We have size, fixed size of the dislocation, and just we took the bias, slanting some fixed bias, and bias is not really essential. The same phenomena exists for zero bias, but it's just random to check that effect doesn't depend on kind of non-essential parameters. And you see that for small chemical potential, applied chemical potential, there is no dip. It's now critical below, critical below, no dip. Once you increase chemical potential, dip starts forming. For bigger chemical potential, it becomes deeper.
But why do you call it chemical potential? It's basically the force that you apply to the string, isn't it?
Yeah, but the point is that it's one and the same. If you introduce chemical potential in the superfluid action, by the nature of Gaussian integration with respect to rho, it immediately translates into force applied to the dislocation.
But which way does it move? How does it move?
Well, it depends how you define chemical potential. There is, of course, some zero when dislocation is not kind of under any stress. With respect to this point, you define chemical potential, but now, with respect to this point, it can go up or down. Chemical potential is something defined, is not really definite. You have to introduce zero, reference point.
Is this even related to Kuklov lap transition where cosine becomes irrelevant in sine-Gordon or something like that?
Oh yeah, it's essentially sine-Gordon becomes irrelevant in some finite range. Once you pass this range, it again becomes relevant. Okay. So what you have in here, basically just to illustrate that for different sizes, different slanting of the dislocations, dip can be present, it can shift to higher temperature, to lower temperature, it can become deeper, but essentially it exists. And also it's a function of chemical potential for different biases. It can only shift, but it doesn't really vanish. Okay, now criticality of the first peak. So what is shown here? It's family of curves of the compressibility. It's a function of chemical potential for different sizes of the dislocations. So you see that for size 60 it's barely visible, but then it starts increasing and shifting to lower values of chemical potential, which is consistent with scaling of the critical, the threshold with the inverse size of the dislocation. Actually, it's more than inverse size, I'll show you. What's interesting is that the height of this peak scales as fifth power of the size. So if you look into, let's say, different known universalities, let's say Ising, this power is at least 3 times, I guess, 3 times higher than possible in terms of interpretation of Ising. Let's say 2 positions, the dislocation, let's say, straight dislocation and bend dislocation, let's say. So this power is at least 3 times higher. Then if you scale, and this is basically how critical velocity is scaled with the size of the dislocation. Dip moves to lower chemical potentials and becomes deeper. And now the position of the dip. Position of the dip is a function of logarithm, perfect straight line with pretty high power. And in naive estimates, which I have shown you before, this power is 1. The power is 1. But it's actually higher at the criticality. And how it can be interpreted is that the gap at the criticality scales inversely with some power of size of the dislocation.
So there's some phase transition.
Some phase transition going on. And just to see what the order parameter for this transition, we can take, let's say, value of response R1, which tells you absolute displacement of the dislocation divided by the applied force. What we see, this is free string. This is free string behavior. Let's say no sign blocking. It's like Gaussian string behavior. It's all normalized to 1. To the left of the peak, at small chemical potentials, if you increase the size of the dislocation, this response function slowly goes to 0. Slightly above the peak, it stays essentially the order of 1.
In your divergent compressibility, if you take the thermodynamic limit, it's a divergent compressibility.
Yes.
The question is, there should be some first order phase transition once the compressibility diverges usually. So I'm just wondering what this first order phase transition might be. It should be quite peculiar in this phase diagram.
Yeah, we were thinking about, originally we thought that there is first order phase transition. But having first order phase transition in 1+1 is a kind of hard. And in fact, we didn't observe any signatures of first order phase transition. So it's second order phase transition. What is it? It's essentially roughening transition. So we can say that below the transition, mean square displacement of the dislocation is essentially some finite number. So it's essentially smooth. Above the transition, it is rough. It behaves like a free string, and this transition is induced by chemical potential.
This is one of the divergent compressibility doesn't mean if you apply an infinitesimal force, you still can compress the system by an infinite amount. So this should be something like the first order transition. So I'm wondering why you don't find something.
We don't see. Well, in the region of peak, we don't see for single dislocation. For single dislocation, of course, there is an issue when many dislocations, and of course, you cannot compress a real sample by infinity. There is a three-dimensional size which cuts it off eventually. We don't know what will be happening at the actual three-dimensional sample, but for one-dimensional isolated dislocation, finite lengths, we didn't find any first order phase transition. There is a hysteresis in the following sense. There is a hysteresis observed for dislocation which is not slanted, non-slanted dislocation, because you have a barrier. And in principle, for if you scan with respect to temperature and away from the criticality yet, you can see some hysteresis, because essentially if dislocation sits in here, it will take time to tunnel. But this hysteresis has nothing to do with actual divergence, which happens at higher values, which corresponds to renormalization of the barrier to 0. So essentially, you can view the transition as an effective renormalization of the barrier to 0, so the dislocation starts fluctuating between two positions quite easily.
So if you were to measure the roughness of the spring, is the roughness peak where that peak was that you showed?
Yeah, both peak. We showed. Yeah.
So the spring is roughest right at that peak?
Yes. 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 Roughest, and its its sort of flexibility or tension is reduced dramatically.
Then it gets higher again.
It's lower.
No, as you go to lower temperatures.
Yeah, if I go away, it gets higher, yes.
So could it be like a depending transition or something?
Yeah, you can view it as a depending transition from sine Gordon potential, yes. Exactly. But it happens only under the application of finite force. Yeah, let me I'm almost done. Now let me show you the actual experiment by Ray and Heller. What is shown in here? Flux rate, which we associate with critical velocity. And at higher temperature behaves kind of normally. I would say that increasing the temperature reduces the flux rate because superfluid fraction goes down. But if you decrease the temperature and come to this region, somewhere here, jump to here, they observed deep. And this is different sample. So we believe this deep has something most likely to do with our mechanism. And the main prediction is if you decrease chemical potential, go into linear regime, it must vanish.
Dip will go to lower temperatures?
No, it will vanish. It should vanish. In linear response, there is no dip. Within the linear response picture, the roughening is not a transition but crossover. Yeah, so this is new sample shown in full logarithmical scale of the for the sample. And you see the depth in this unique sample is pretty high. And we wonder if this is essentially something which we kind of predicted. And so the main prediction is that this dip should vanish if Heller enters essentially a linear regime of the response. It's important that away from the dip, response is linear. Response is linear essentially. Only close to the dip it becomes essentially nonlinear. So the main point is that combination of Pyle's potential and external stress, or chemical potential, produces strongly nonlinear resonant behavior of this ring. A wide range of applied chemical potentials. And this resonance shows up as a peak in compressibility and as a dip in the critical superflow rate. So we believe this was observed already by Ray and Heller. So the key experiment is measuring the flow rate versus applied chemical potential at fixed low temperature. And the question actually, which we are trying to understand, the universality of this roughening transition. So I believe that the temperature where this peak is observed is still essentially zero temperature. Since it's finite size system, it's essentially a chemical potential driven transition. So the graphs I showed you were in the range where rho s were not affected. It means essentially zero temperature. Okay, thank you.
I'm a little bit confused about this chemical potential versus applied force thing. So what do you actually have to do to change in an experiment? So if you have the experiment with a dislocation, pin this, you want it to be pinned. So what do you actually have to do in order to apply this force?
Okay. There are two ways applying chemical potential or force. In our model, force and chemical potential is the same, because it's up to Gaussian transformation is the same.
But is chemical potential the original bosons, or when you say chemical potential
well, it's
of what?
Because when you shift chemical potential, you essentially try to increase the density, let's say increase chemical potential, you try to increase the density, but instead of that, dislocation simply moves. That means that you do apply some force to move the dislocation. So it's...
So I'm just confused because I can imagine an experiment in which you have this a dislocation in the middle of your sample. So up and down are sort of symmetric. So there is no broken symmetry in this respect.
Right.
And so then you're basically changing the density, and you're saying it selects up from down. Because this force must have a sign, right?
Yes.
Plus or minus.
Right.
How does it know which sign to put?
Okay, let's say your sample contains single dislocation.
Yes.
And this single dislocation is in equilibrium with some reservoir, superfluid reservoir. And chemical potential here and there is the same. And let's presume this dislocation doesn't feel any stress because of the difference of chemical potentials. It's just straight. So now we say, okay, this is the condition where chemical potential is zero. Let's call it zero. Let's call this chemical potential zero, right? Now, let's apply some pressure on the reservoir. It means we try to increase chemical potential of the bulk. It means that the dislocation will go essentially down. If we try to decrease pressure on the reservoir, we decrease chemical potential and dislocation will go up. It will get rid of particles. So if particles come in, dislocation will go down. If particles go out, dislocation will go up, presuming the half plane is here. If half plane
injected from some half plane.
If half plane is here, it will be just the opposite behavior. If you consider two dislocations, the response will be completely opposite and there is no broken symmetry as you mentioned. But symmetry is already broken by the half plane.
So I want to ask you this question again, because the particle's potential in direction perpendicular to the screen, because the dislocation is much smaller than this one. So basically dislocation is much softer in that direction than in this direction. So, and you very easily create kinks in the direction of perpendicular to the screen than in this direction, and that doesn't require any mass transfer.
Yeah.
So I would expect that fluctuations, which involve this coordinate would strongly renormalize all your parameters, and that might change all temperature dependencies.
Yes, yes. We basically considered two models, for pure glide and for pure climb.
No, but now you have a
Now we have to consider combined model, and this is what we are doing now. Yes, absolutely.
So when the string roughens, is it harder for the superfluid to move along it?
This is also a good question, which we try to answer from first principle simulations, because this is model simulations. We cannot handle big strings with ab initio simulations. But this is a possibility, that actually when you have kinks or jogs on the dislocation, there is a mechanism which kind of lowers superfluid stiffness. Of course, by hands we can put some term which, but in a minimal model, there is no big effect of roughening transition on the superfluid fraction. There is some, but it's not critical. So criticality is not seen in superfluid channels.